I am Nagarajan Sridhar, Product Marketing Manager for Isolated Power Products. What do you see when you open the hood of your car? An engine block and control, which is the heart of the automotive system, along with the battery, some motors, and tubes. You would also feel some heat radiating, especially after driving your car for a while. The reason being, the engine system, also called the powertrain, operates at temperatures exceeding 125 degrees Celsius. Before we go into this discussion, we need to understand the current and the future trends in the automotive market. Over the last couple of decades, more and more electronics are being added into the automotive system thanks to the component miniaturization. These additions have gone primarily into low power systems such as sensors and infotainment, thereby making the car smarter and more fun to drive. While the trend of electronics in the infotainment systems continue, a future trend in electronics is the powertrain systems like the engine blocks and controls. This is made possible due to the advances in power electronics. The reason for this trend is fuel efficiency standards mandated in several countries across the globe, and that is increasing. To be clear, the fuel efficiency is measured in terms of miles per gallon for fuel injection vehicles and miles per charge for electric and hybrid electric vehicles. So, why power electronics? Power electronics transfers power very efficiently and occupies much small space, making the car lighter. A lighter vehicle improves the overall efficiency, meaning improved mileage, and also power electronics replaces mechanical parts, improving the reliability of the vehicle due to lack of moving parts. Now, as the space or size comes down, the power density gets higher. This is true for high power transfer in the kilowatt range, typical of powertrain systems. The problem with this is heat dissipation. So, in a nutshell, reducing the size of the system and managing the thermal issues are key factors towards improving fuel efficiency. Using commercially available electronic switches such as MOSFETs and IGBTs based on silicon, there are limitations to overcome. For example, silicon based power switches suffer from reverse recovery and breakdown issues at high temperatures. Therefore, if one were to use silicon based switches for the power electronic circuits subjected to high temperatures, cooling systems such as large copper blocks with water jackets need to be added. However, this will result in the size, weight, and the cost of the vehicle increasing. The wide bandgap semiconductors, such as silicon carbide, have much higher operating temperatures, known as the junction temperature. Thermal conductivity, that is 2 to 3 times higher than silicon, higher breakdown voltage, and capable of switching at much higher frequencies, which with negligible power losses. The higher operating temperature of the silicon carbide allows the circuit to be placed close to the location where the temperatures are high. The high thermal conductivity of silicon carbide eliminates the need for big copper blocks and water jackets. High switching speed in the megahertz enables the overall power circuitry to become smaller in size. A gate driver is needed to switch silicon carbide FETs efficiently. An example of such a gate driver is our recently released UCC 27531. The UCC 27531 product drives the silicon carbide switch at the desired operating voltage and has the ability to handle negative input voltages, features that are critical for noisy environments. For more information on power electronics that drive silicon carbide power FETs, go to the following URLs. Thanks for watching.